All right, welcome to our review session for today. I'm Jared, and today we'll be covering simulation. All right, clear off my R browser here. Maybe we'll start over there. I'm Jared, and today we'll be covering simulation in our review session. If you have questions on time series for this week's homework, please see the recorded video from last week's R Help session on time series. All right, so for simulation, what we're doing is we're taking something that we can define with some distributions or some randomness and seeing how often things happen over several thousand iterations, or we can even do several million iterations. We could just generate some things from random normal distribution, except oftentimes we want something a little more complicated or interactive than just normal draws. So an important function to know how to use is the replicate function. All the replicate function does is it does a command, in this case 10,000 times. It'll do whatever you ask it to, and then it will save the last piece of output. So if I run these inside two lines here, 1 plus 1 is going to give me 2, and 4 is just going to give me 4. So if I run the whole replicate function here for example 1, and I ask for the statistical summary of example 1, all I have is 4s. All right? That's because everything inside these curly braces right here is calculated, and the last output value is saved to an entry in this vector example 1. All right, so example 1 is a vector. We look at the first 10 entries. Called example 1, not example, sorry. Look at the first few entries, they're all 4s. All right, not that we really care to get 10,000 4s in a row, but what we care about is to demonstrate that the replicate function does whatever it tells you to and saves the last piece of output. Okay? So let's simulate something. How many heads do you get on 2 fair coin flips? So a coin flip, heads or tails. It's 50% heads, 50% tails. If we want to count the heads, we can use the R binom function. R binom gives us a random binomial. All right? So what this says is I want to do 1 coin flip 1 time. And there's a 50% chance of heads. In this case, there's a 50% chance of 1 and a 50% chance of 0. So this is P, the percent chance of 1. Okay? So I have a first coin flip, a second coin flip, and then I'm going to add the two together to see how many heads I get with 2 coin flips. So I run this 10,000 times by running the replicate step. The summary is now basically what you would think. I have 25% zeros, 50% of them have 1 heads, and 25% get 2 heads. That's what we would expect, right? All right. Slightly more challenging example that connects more to your homework assignment. You and your sister take turns walking the dog every day. You figure you end up doing it about 70% of the time. When you go walk the dog, you walk a normally distributed distance with an average of 2 miles and a standard deviation of 0.1 miles. So there's a random quantity to how long you walk your dog. How much do you walk on an average day? So we can't just use a random normal distribution for this, because some days you don't walk the dog at all. In fact, 30% of the days you don't walk the dog at all. So to simulate it, we're going to take a variable called dog. That's going to be a random binomial. We're going to do a single quote-unquote coin flip. We're going to do just one of them. And we want a 70% chance of heads in this case, right? Because you have a 70% chance of walking your dog. Then, if you do go for a walk, we want a single random normal variable with a mean of 2 and a standard deviation of 0.1. And now for our output, we can multiply the 2. Why multiply the 2? Well, if we don't walk the dog, that random binomial is going to be 0. And 0 times whatever this is going to be 0, which is what we want, right? If you didn't walk the dog, you didn't walk any miles. If you do walk the dog, then dog times walk will just be dog. Make sense? There's other ways we could do this with if statements, saying if you walk the dog, then record the mileage. But this is the same. So we have an average of 1.4 miles walked. Notice that's not 2, because we have to account for all of the, what we call probability mass at 0. We could have calculated that by hand if we wanted to do that on the board with, with numbers and expectations. However, the standard deviation is going to be a lot more complicated than just taking an average across variables. And in this case, our standard deviation is 0.9, which we can easily calculate a simulated value. So when I say our standard deviation is 0.9, I should say it's approximately 0.9. Yes? Absolutely. So I'm going to pull up the help page here so that it shows you exactly what we're dealing with. So for a random binomial, we have n, which is the number of samples you want out of the binomial. Okay? Then we have size. What size is saying is the number of coin flips in each sample. So if we want these to be Bernoulli trials, size equals 1. All right, we could have 50 Bernoulli trials, so n could be 50, size is 1, and then peak prob is our probability. So for a point of a simulation like this, it's just 1 and 1. Into your second question, our norm has the same, Our norm has the same entries as p norm and q norm have before, except the first entry is the number of samples you want. So we want one sample, one random draw. We want a mean of 2 and a standard deviation of 0.1. It's almost the same equation we used before, except for p norm, we told it what value we want to integrate to. For q norm, we told it how much we want to integrate. And still the second and third are mean and standard deviation. Does that answer your question? Excellent. So did you have a question too?
So what would be the difference between one coin flip 2 times and just 2 coin flips 1 time?
That's a great question. Let's look what happens. So if I do 2 coin flips 1 time, right? So one instance of 2 coin flips. You need a comma there. The probability of 0.5, I get the number 2. Whereas if I do 2 separate coin flips, right? So this 2 single coin flips, I get 2 zeros. So the difference being, this will return 1 single number, right? Because you only had 1 sample, and you're counting the number of heads there. This is doing 2 separate samples of a single flip. Now in the end, if you were to sum over this, you'd get the same thing. So really, instead of, on our previous question, instead of doing 2 separate flips, we could have done either of these 2 commands. In this case, all roads lead to Rome. Did that answer your question? Okay. Any other questions on the dog walking example? All right. What's important here is that we are not using a single distribution, but we're imposing some restriction on our normal distribution. All right. Example 4. Let's say you work at a baseball stadium and you have about 2,000 seats, so you have 1,500 water bottles. Well, it's a hot day and demand for water bottles is high. In fact, it follows a gamma distribution with a shape of 5 and a rate of 1 over 200. You have 1,500 water bottles. What's the probability you sell out of water bottles? All right. The gamma distribution, it's not one we talk about a whole lot, but it's a positive-only distribution. It's impossible to have negative values. That's what makes it good for something like demand in this case, right? You're not going to have negative demand, at least on a simple problem like this. However, we still have the d, p, and q functions like we did for the normal distribution with p norm and q norm. So if we really wanted to, for the probability, we could just ask for p gamma, integrate up to 1,500, and we'll give it the shape and the rate. Those are the 2 parameters for a gamma distribution. You don't have to worry too much about what they mean, but for your homework, you do need to know how to plug that into one of the gamma functions, which I show here. All right, remember that this integrates up to, so there's an 86% chance that we have enough water bottles, and 13% chance that we don't. Absolutely, that's a good question. Actually, let me draw it in R, because then everyone at home can see. So I'm using the curve function like you did on your homework last week. I'm giving it x as the variable I want to be drawn over. I'm giving it the shape and the rate, which are our two gamma parameters. And I'm going to go to 2,000. Actually, we only have 1,500 water bottles, so let's do that. Okay, that's what it looks like.
So the P gamma without the 1 minus, what gives you what part of the curve?
So with the 1,500 there, excuse me, not horizontal, we want it vertical. So P gamma, all of the P functions, P norm, P gamma, P unit, or whatever function it may be, integrate from the left up to a point. If we want the probability we sell out of water bottles, that's the probability of being greater than 1,500. That's why we do 1 minus. All right. I show you this piece, not because that's directly applicable to your homework, but to get you comfortable that gamma is not too different than normal. It's just positive only. So let's get to the actual simulation. How many do we expect to sell? So in this case, we're going to do, once again, do 10,000 replicates, just like we were before, except inside of our curly brace, we're going to simulate a demand. In this case, demand is going to be a random gamma variable, the shape of 5, so one of them that has a shape of 5 and a rate of 1 over 200. And then how many do we actually sell? Well, we sell either the amount that were demanded or 1,500, right? We can't sell more than 1,500, right? That's all we have. So the output I want from this replication is the minimum of the demand and 1,500. So now when I run this, I see that on average we sell 952 water bottles. And the histogram of all possibilities we get from the simulation looks like this. So sure, on average, we sell 950 water bottles, but quite frequently we sell out. You see the large column for selling out there? Cool. All we're doing is taking something that's more complicated than the distributions we've discussed, doing it several thousand times so that we get a distribution of something new. Because this is a distribution, we can take means, standard deviations, do histograms, everything you know and love. So a few notes on this same problem. Some of your professors and some of your classmates may, instead of using the replicate function, they may just use a for loop. That's perfectly fine. They do the same thing. If you're using a for loop, you're going to need a place to store your information. So we're going to create an empty vector of size 10,000. You can just use a numeric function to create an empty numeric vector that has 10,000 slots. And then we're going to loop over those slots. So we're going to do this one at a time. So we say for I is our index, that in I let I go from 1 to 10,000. And then, notice the curly braces again, what are we going to do for each of those values? Well, we're going to generate a demand, just like we did before. And then we're going to find the minimum of that demand in 1,500, the number of water bottles, right? Except now we have to tell it where to store that. So we're going to store it in the ith entry of our empty vector. Okay? When we do that, we get about 950 water bottles again, on average. So you may notice that this did the exact same thing as what we had before, but with an extra step or two. So if you need to do the exact same thing independently lots of times, then replicate is probably simpler to use. If you ever need to do something a little more hands-on, or if you ever need your iterations to talk to each other, note the word independently here means that this can't communicate, right? If you ever need your iterations to learn from the previous iteration, you probably want to use a for loop. One other customization you may see in your code, or code of professors or friends, is instead of the minimum, they could use an if-else statement. Right? So here we have the same replicate code from before. Here's our demand from a random gamma. Instead of the minimum, we can now say if else. So this works just like the function does in Excel. Or like the if, I think it's just called if in Excel. If demand is greater than 1500, return 1500. Otherwise, return demand. Here we're doing, this is the exact same thing as the minimum function. Right? We're just going to return the smaller of those two numbers. But this is also customizable if you ever need something with a more complicated logic statement in the first piece there, in the first argument. This is the function to use.
Do you have to know all three, or can you just do the replicate?
You can just do one of these. That's why I've called this 4B, 4B, and 4C. They all work just the same. I wanted to explain here because if you compare code with people at any point in time, there's lots of different ways to do this because you're just telling the computer to do something a lot. Okay, any questions on the water bottle example? Any further questions, I should say. All right, example 5. Let's get a little more complicated. You are running a used car dealership. You buy cars for anywhere between $12,000 and $18,000. You do anywhere between $0 and $1,000 of repairs, and you sell them for anywhere from $15,000 to $20,000. Obviously, to generate a profit, you need to buy and repair them for less than you sell them for. If we don't monitor that closely, what's the chance, or what's the average return you'll get off one of these car deals? So we can replicate that as well. Here we have our unif. Our unif is a random uniform variable. Uniform meaning instead of the, there's no markers here. Instead of a normal distribution, right? Instead of a pretty bell curve like we get with a normal distribution, a uniform distribution is just a block. So in this case, it's a uniform 0, 1. So we have equal probability for all values between 0 and 1, and no probability for any values outside of 0 or 1. So in this case, we're saying for prices of used cars we're going to buy, that price could be anywhere from 12 to 18,000 with all equal value. The number of repairs, the dollar figure of repairs that we do is anywhere from $0 to $1,000. The sell price is anywhere from $15,000 to $20,000. So here we're just going to pull values for these three amounts. So for example, our buy price is $14,600. We're going to do a fair amount of repairs to it, about $670 worth. And in the end, we get to sell it for $19,000 and change. This would be a pretty good investment as a used car dealer, this particular combination. Of course, in the real world, these are correlated. We can do correlated values later if you really want to. But for now, we're going to randomly sample these three things and find out what the distribution of profits looks like. Right? So the profit in this case is just the price you sell it for, minus how much you repaired, minus what you bought it for. Right? Pretty straightforward. So your average profit on one of the cars is just under $2,000. Your standard deviation is just over $2,000, which means you do have a fair chunk of the time where you don't generate a profit on your used car. So perhaps there's a better way to run this business, right? In fact, how would we calculate what proportion of cars failed to turn a profit? This last week on the homework. So if we take our vector of example 5s, we want to find out how many of them are greater than 0. So if we ask for the amount of, if we transform the vector, so transform is probably a taboo word because we use that for logs and things in regression. But if we ask R which of those are greater than 0, and we sum over that, we get that 7,800 of them generate a profit. So if we divide by 10,000, the number of the total, we see that 78.58% of the time, this car business has a profitable transaction. Fair enough? All right. For our last example today, it's actually a problem to work on. Let's say you only had $50,000 to invest. What's your expected result as a used car dealer? So in other words, you need to go buy so many cars. And let's say at any point in time, the cars are all the same price, for simplicity's sake. So there's some car price, there's some repairs those cars need. Let's say all the cars need the same amount of repairs. So you're buying these cars in batch. You can buy up to $50,000 worth and then try to flip them later. How would we do that? Well, first question is, can we use the replicate function? If you recall, we need a for loop anytime we need to do something where each of the samples or each of the simulations is not independent. Are these simulations independent? The simple answer is yes. And this isn't independent in the statistical world, in the statistics version of the phrase. I mean independent as in, if you draw one simulation, does your next simulation need to know anything about the previous? And the answer is no, because we want to simulate this across a whole bunch of different possibilities. So yes, we can use the replicate function. All right. Well, what about the replicate function? So what's the first business exercise we need to do on a given day for this used car dealership? We don't have any cars, but we have $50,000. So what do we do? Just pocket the 50 grand and walk away. Yeah, thank you. We need to go buy cars. All right. How many cars can we buy? Well, there's a random price, right? So for the sake of this example, we're going to have a single car price for the day. And that car price, as we said before, is a random uniform from 12,000 to 18,000. Okay? All right, in this case, our car price is, pretty high today, almost 18,000. How many can we buy? The car cost 18,000. How many can we buy with 50,000? 2.5. Thank you. So we actually can't buy half. So what do we do? How do we tell R that we can only buy 2? Well, first question is, how'd you get 2.5? Great. 50,000 divided by car price. However, we can't buy half a car, so we need to round down, right? We have to always round down. There's no rounding up here, unless you can get more cash. So in R, there's what we call the floor function. So floor takes whatever number you give it. Right? Usually we'd round that up. Floor rounds it down. Similarly, if you told it ceiling, it would always round it up. So in this case, the number bought is going to be the floor of the number of fractional cars we can buy. Right? Like she said, 50,000 divided by car price is 2 and a fraction. We ask for the floor of that. We get just 2. Great. Now we need to repair the cars, right? Maybe not repair them, but we need to go detail them and spiff them up because we're selling them at a dealership. We should probably bake that into the actual car price, right? Before we buy them with our limited budget, we should probably think about the fact that there's some amount of detail we'll have to put into the car. So I'm going to add, oh, it's down here, sorry. I'm going to add our repair cost to the original car price. Now, given the stark difference between the small dollar value of the repairs and the larger price of the car, I probably won't need to worry about that too often, but we want to make sure that this is a functioning business and we don't run into situations where we can't fix the cars we buy. So what if we do that instead? Well, it's only $1,000. Oh, with a lot of repair price today, I guess. So let's run it again. So now our random car price plus repair cost on this instance is close to 17,000. We'll run this next line again just for demonstration. We still have 2 cars. All right, so now we have 2 cars. They are bought and they are repaired. What do we do next as a business? Han, what would you do next? Sell the cars. Yeah, it's hard to generate a profit if you just have cars sitting there. All right, so we need to sell price, right? So if we look back up here, we found out our buy price, we repaired the cars, and then we can sell them for a certain price. We assume we have sufficient demand for whatever price we choose in this case. As I hope you've been able to see, if we need to make these more complicated, we certainly can. All right, so our new sell price is going to be somewhere from 15 to 20K. Hopefully it's on the higher end because otherwise we're going to go broke on this given day. All right, good news. We have a really good sell price. We're close to $20,000. All right, so what's our revenue? How do we calculate revenue in a product market? We just have our price. In this, usually we'd say number sold. In this case, we assume the demand always meets. So we have our price times the number bought. Okay? Our revenue is 39 grand, or almost 40 grand, right? Pretty good day. Is this our cash on hand at the end of the day? Are we done? Or do we have extra cash? Yeah, we still have our startup. Well, we still have a few grand from our startup money for the day. All right, so let's call this end of day. All right, so at the end of the day, we have our revenue plus how much? How much did we spend to begin with? Well, we had 50,000, and we spent how much? Well, we bought 2 cars, right? How much did we buy them for? The price of the car. Great. So at the end of the day, we actually have $56,000. If I could earn $6,000 a day, that would probably be pretty good, right?
Why are you adding the 50,000? Didn't you invest that in something?
We did. So right here we have what could be an intermediate calculation. So right here after we buy the cars, we can say we have leftover cash, right? And then at the end of the day we have our revenue plus our leftover cash. Does that make sense? All right, we want this to return our end of day, and we want to simulate 10,000 of these days to see what our business model looks like. That was pretty easy. Instead of dragging that down 10,000 columns of Excel, we just hit enter. Well, let's check this out. What's a histogram of our big example? What's your favorite color? Sorry? Blue. All right, that's a good color. Okay, so here, kind of a stark blue. Let's go sky blue. So you can see the lines in between the bars. Every day that we earn over $50,000 means a day we generated a profit, right? How often does that happen? Well, let's count the number of our big examples that are greater than $50,000 and divide by 10,000. 78% of our days, almost 79% of our days, are profitable.
Does it matter if you put the end of day thing at the very end?
It's a good question. I'm not sure. Nope, it doesn't. Thank you. I learned something. I guess it goes with what I said earlier. It's whatever you write last is stored.
Should we
Yes.
go down? I got 3 for number of cars, but
Yes, sometimes you'll have 3 cars. For example, if we take, just for kicks, let's comment out all of these lines. Remember, comments is the pound sign or hashtag will probably be only known as 2 years from now. This is now our distribution of cars. So over half the time we buy 3 cars. Occasionally we can afford to buy 4. The rest of it we can afford to buy only 2. See, all I did here was we are now calculating the number of cars we can buy as opposed to the rest of the formula. All right, that's the material I've had prepared for the day. I can now take further questions you have on this, or we'll end the video.